Good evening, everyone, and welcome to another edition of Virtual Starry Skies. My name is Joe Aiken. I'm the technical director of the Tongue Visualization Lab. And again, hope you guys are all doing well this Friday evening. So we're always going to start off like we do every week with just a kind of take a look at our nighttime skies. So we're going to start off by bringing down our title. And let's just see what we can see here. We always like to start off in the west. Okay, so looking up, it looks probably very similar to what it did last week, with kind of a big change. Because for the longest time over the last 2 months, you've probably been seeing a very bright object doing its little dance in the west. It is now very low on the horizon. In fact, you probably won't be able to see it over the next couple of nights. And that is, of course, the planet Venus. It is now gone behind our horizon here because we have a lot of hills, of course, here in central New York. But there is another object that is now visible. And of course, you got the moon up there. There's going to be some of the brightest things up there tonight. Over the next couple of nights, it's going to get brighter and brighter as it starts heading to a first quarter and eventually a full moon over the next week. But there's another object, and it is right here. Let's go and take a circle of it. That is indeed the planet Mercury. And we very rarely do we actually get to see Mercury, and it made some really nice pairings over the week. If you went outside and looked to the west, you might have noticed it was right next to the planet Venus, and then slowly moving away from Venus, and it actually paired with a crescent moon a couple of nights ago. But let's go and scale it up, and here you can see Mercury. If we were to look at it with a really powerful telescope, of course you really can't see that from Earth with any ground-based telescope, but here you can see Mercury. It's about what we call, I guess, a first quarter phase for Mercury. About a quarter of it's visible from the Earth, but of course half of it is always visible. But Mercury is actually very low in the west. Very cool object to see. So on the next clear night, go out, take a look at the west, northwest, and you will see Mercury. So definitely go check it out. Okay, so today we're actually not going to be talking about planets. We're actually going to be talking about smaller objects in the form of what we call minor bodies or minor planets, or in fact, asteroids and maybe some dwarf planets, and of course, comets. So let's start off by letting our sun go down, bringing out those stars. But to get a better look at some of these smaller bodies, it's kind of hard to see them from the Earth because they don't really reflect a whole lot of light. So we have to fly away from the Earth and look above our solar system. So hold on to your seats. We're just going to fade down some of our scenery here. And let's actually take a flight out of the Earth and look back at our solar system. And I'm going to turn on a couple objects here. One, the orbits of all the planets. You're going to see some other kind of regions start to be highlighted. And I'll talk about each of these once we get out here. There we go. So now we're looking down on our solar system. And you can see a couple of regions here highlighted. The bright green region right there at the center, that's actually where most of our asteroids are located. These are what we call main belt asteroids. You might see a red region in between, like in between the sun and that green region. Those are also technically part of that main belt asteroids, but they have weird orbits, and they actually indeed cross the Earth's orbit at times. Or get close enough where we actually call those near Earth asteroids, and we'll get to those in a bit. You might see some weird lobe features around some of the planets. Those are actually what we call Trojans. The light blue-green area outside of that green area from basically the orbit of Jupiter through Uranus, and actually really between kind of Saturn and Uranus. Those are what we call centaurs. And then from Neptune and beyond, those are Kuiper belt objects. So I'm going to talk about each of these regions. We're going to get a little bit closer in each one as we go along. If you can see my cursor here, I'm just going to use that to kind of point things out. So again, Those are the main belt asteroids that we're going to focus on first, and we'll get to these other regions in just a bit. So, first off, let's take a look at where these asteroids are. I'm going to put a whole bunch of them on. Now, these are all the asteroids that we have cataloged in our system. They're usually updated. I usually try to update them once a week or so. So currently, there are over 950,000 asteroids that we've cataloged and named. Of course, that number is always going up because we're always finding smaller and smaller objects, and we're just be able to, more people are looking up the sky. We have better instruments, better spacecraft can actually detect many of these objects. And just kind of talking a little bit about these asteroids, I mentioned it before. Asteroids do not reflect a whole lot of light, and they definitely don't give off light. Remember, the only things in our solar system, or actually in the universe, technically, let's say in our galaxy, that give off light are stars. Everything else reflects light, even the Earth. It reflects the visible light. So asteroids and, I dare say, comets, we're going to talk about comets too, they don't reflect very much light at all. So it's really hard to find these things. So there's a couple of methods astronomers can use to actually try to find some of these asteroids. Sometimes it's actually just luck of the draw. They're looking at something else. For instance, one of our professors here at Colgate, Tom Bolanek, and we'll get back to this discovery in just a bit, but he was actually looking at distant quasar objects, and something went into his field of view, created a streak on some of his photographs, and lo and behold, it was an asteroid. There's a little bit more to it than that, but a lot of them were actually found by accident. So let's go a little bit deeper into some of these features and some of these regions that we find. We're going to start off again at that main belt. So we're going to fly back in. Let's go and take away some of these regions and get a little bit closer here. Now, if you don't know the planets, we'll kind of take a look here. The first one that's kind of spinning really fast is Mercury. Next one out is Venus. The blue orbit there is the Earth. The next orbit out, you can barely see it here where my cursor is. That is the red planet Mars. And then here are all those asteroids. And then here is this white orbit right here is the planet Jupiter. So as you can see, most of the asteroids are in between Mars and Jupiter. And so let's kind of take a look at some of these as we go along. There's actually several types. You know, astronomers always like to group things together and categorize different objects, kind of like objects with like. So some of the types, I'll kind of talk about each one. 75% of the asteroids that we discovered are what we call C-type. That's the letter C. Those are actually made mostly of like this carbonaceous material. Think of large amounts of like carbon and kind of more of those kind of heavy elements deep within the rock structure itself. They usually have a very dark hue to them, and they actually make up mostly of the middle part of that asteroid belt, if you will. So all those kind of rocks that are kind of in the middle. Usually they have large amounts of water molecules. Again, not very reflective, but those are some of the types that you might get kind of larger in structure. Now, some of the lighter rocky materials that we might find that might contain iron, I guess it's just a heavier, strike that, a little bit heavier materials like iron, magnesium, nickel, silicates, like any type of silicon type rock structure. They make up about 17% of the asteroids in the asteroid belt. And those are what we call S-type. And then there's actually rare forms where you might find some of these precious metals, like the metals that we find here on the Earth, like platinum. Very rare metals actually can be found in some of these rare asteroids in the asteroid belt, and those are actually what we call M-type, and those are actually make up the rest. So not very high percentage at all. So they're actually very precious when we do find them on the Earth in the form of a meteorite or so when we find some of these M-type. Now, of course, there are several groups here. We're going to get to some of these groups in our next section here. Those red dots that you see kind of orbiting closer to Mars and Earth, those are actually a subtype of the main belt asteroids. This is called a group called the Hungaria group. And they actually have, they're in this weird region just outside of Mars. And it's just due to gravitational forces between the sun, Mars, and Jupiter that keep those asteroids kind of in stable orbits, right around the orbit of Mars. And those are called the Hungaria. We're going to come back to those in just a bit. Okay, so, and actually in the Hungaria, we've discovered a little over 8,800 or so asteroids in this group. Now, you might wonder, like, where do some of these asteroids get their names? And there's actually really funny names. The planets are actually, there's usually a committee, the IAU, International Astronomical Union, that actually has criteria to name planets and moons. Asteroids is kind of free flowing. They let people who discover them name what they like. Of course, they rather not have planets named after pets, but that did happen. There's actually a whole asteroid named Mr. Spock, who was named after a person's cat. And so we have a Mr. Spock asteroid. And, there's other ones like Frank Zappa. There's a couple asteroids named from the Columbia shuttle mission that burned up back in 2002. But, and we're going to come back to this in one of our examples. There's actually an asteroid founded here at Colgate, and our own Professor Tom Balanik actually named that asteroid. So before we do that, let's take a look at some of the sizes and shapes of these asteroids. We're going to start off looking at the four largest. We're only going to focus on the first two here. But you have, first of all, let's take a look at Ceres. We're going to look at Vesta. Those are the first two that we're going to actually take a closer dive at. Because Ceres is actually an interesting object. It's now no longer classified as an asteroid. It's what we classify as a dwarf planet. In fact, when it was first discovered, it was originally considered a planet. Its classification has been changed quite a bit. And we'll actually go diving into that now. So let's go and fly over to Ceres to get a closer look here. And there we put the orbit. That's that little white orbit there, kind of just outside those red asteroids, right in the main belt. So let's take a closer look in. All right, so here we have the dwarf planet Ceres, because Ceres is actually very, very large for an asteroid. If it was going to be considered an asteroid, it's actually nearly twice as big as the closest second largest asteroid, and that's Vesta. So Ceres is a little over 900 kilometers in diameter, very, very massive. But you got to remember, it's still smaller than our moon. But it is round in shape, as you can see. But it is filled with lots of craters, covered in lots of kind of rich silicate minerals and ice. There's still a lot that we're trying to figure out about Ceres. There's like weird salty kind of features on the surface as well. So really interesting compounds here on Ceres. But it, again, is considered a dwarf planet. And it was discovered back in 1801. But reclassified as an asteroid in 1850s, and then recently reclassified again as a dwarf planet. All right, but Ceres has a nice stable orbit in this asteroid belt. The idea is that, if this object was actually by itself outside of the asteroid belt, it would probably still be considered a planet, because if it kind of cleared out its debris field, of course it didn't, and here it is stuck in the asteroid belt. So let's fly out a little bit here. And we'll move on to our next asteroid, and that is, of course, the planet Vesta. So let's head on over to Vesta here. And we'll fly out a series of more. Vesta, again, is the second largest object in the asteroid belt, founded in, actually, first by mathematics, doing what's called the Bode's Law, and discovered again by mathematics, because looking at gravitational interactions, looking at the orbits of Jupiter and Mars, they said there has to be something there in between the two. And then when they went hunting, they actually found Vesta. And again, roughly discovered in 1807. And they also discovered Pallas around the same time as well. That's Friedrich Gauss, and of course, Olbers was the one that actually initially discovered Vesta. And what's interesting about Vesta, one is its shape. It's not round, so we would not really consider it a planet. And it's not quite big enough to have that round shape. But what's interesting, there might be fragments from the asteroid belt that might have once belonged to Vesta. And that's something that, astronomers are still trying to figure out. Maybe a lot of these fragments in the asteroids do belong, if you kind of piece them all together, to one object, either Ceres or Vesta itself. The Dawn spacecraft actually visited, did a little flyby of Vesta in 2012. They found a surprising amount of hydrogen actually on its surface. And we think it might have been leftovers from whenever it first formed. But so that's a very interesting object there in Vesta. So we're going to run out of time, so I got to keep moving here. But there's plenty of mountains and valleys here on Vesta, especially in the South Polar region. There's a mountain here that reaches over 65,000 feet, about 20 kilometers in height. It's nearly as tall as Olympus Mons on Mars. Again, this is on a tiny object, only 500 kilometers across, and there's a mountain that's 20 kilometers high on it. So very big features here on Vesta. So there you can see the kind of mountains sticking up over the surface there. Okay, so let's fly out of Vesta. Again, the second largest asteroid in the asteroid belt. And our next asteroid that we want to visit is kind of a strange looking object, and it's called Eros. And this actually, Eros was visited by the Near Shoemaker spacecraft back in 1998, and it was actually one of the first asteroids to actually be studied from orbit. And it was actually first discovered by Carl Gustav Witt at Berlin Iranian Observatory back in August of 1898, August 13th. And of course, from the Greek mythology, the son of Aphrodite. And so here you can see this weird shape that Eros has, almost like a giant potato. We put some light on here just so you can see it. And let me get us kind of oriented around here just so you can see it a little bit better. So Eros is actually one of the few asteroids that's been studied up close, of course, by the spacecraft. Astronomers actually, there's a lot of kind of 3D printed objects from Eros. You can actually download those from the NASA website. If you have a 3D printer, you can actually print them yourself. But yeah, so Eros again, just kind of a fun little object I wanted to point out. And it's actually not very big. It has, along its longest diameter, it's about 16 or so, a little bit more than 16 kilometers wide. All right, so our next object I want to point out, it's actually two objects. And that was, of course, the pair called Ida and Dactyl. Galileo spacecraft launched to head to Jupiter, actually flew by this pair back in 1993, in August of 1993, and actually captured a really cool image because at first we didn't think that it had a pair. So right now we're just showing the one model here. This is Ida. It also looks kind of like Eros, very potato shaped, very oblong. But what's cool about Ida, it actually had a partner with it. And we're finding that a lot of asteroids come in pairs of two or more. And here's an image of Ida and its little partner and companion. You can see that off to the right. That is the little object called Dactyl. So this pair is actually, there are craters on the surface that we thought, looking at some of these craters, you might think it's kind of old, but there's actually some weird material that makes it look maybe has a younger surface. So we're still learning a lot more about Ida and Dactyl. And it was actually first discovered in 1884 by Johann Palisa at the Vienna Observatory. And this Dactyl actually wasn't discovered until 1994 from the Galileo imaging team. And so let's move on. Now, so there's Ida and Dactyl. Now, our next object is actually discovered by, again, our own Tom Balanik. This is the name of John Euler, and it was discovered here at Colgate at our Foggy Body Observatory in 1991. And this is actually kind of a fictitious model. Unfortunately, we do not have a real model of this asteroid. Maybe soon, because it is a very faint object. It's really hard to see. And it's actually named in honor of John E. Euler. He's a dedicated and highly respected teacher of high school physics, educated at Penn State and the University of Buffalo. He also taught physics and chemistry over a 33-year career, and it was actually Balanik's high school physics teacher, taught from 1959 to 1984 at East Ridge High School. And Tom says it's dedicated because his animated demonstrations inspired generations of students, himself included. And here's actually the image of that Balanik took. Let's see if I can get this to work here. And so this is how some astronomers actually do discover asteroids. They're looking at photographic plates, again, looking at comparing stars. You see on the right, the little tiny dot of the asteroid, and you just look for tiny motions and look for little streaks in the images. And so here's the John Euler, again, discovered in 1991 by our own Tom Balanik here at Foggy Bottom Observatory. All right, well, let's take a look at some of these other regions of asteroids. We're actually going to zoom back out just a bit and come back into and look at what we call near-Earth asteroids, and a subgroup of those called potentially hazardous asteroids. And they sound very scary because sometimes they can be. So let's zoom back out here. All right, we'll wait for this to do its thing. And let me turn on some of these objects here. Now, all these objects, as you can see, these purples and greens and kind of light blues. Here, I'm going to zoom back out just a bit just so we can see it. All these objects actually intersect Earth or get close enough to Earth where they could potentially be a hazard. To date, we have found over 10,000 near-Earth asteroids. Of those, a little over 860 are actually over 1 kilometer across that could cause mass devastation. About 2,000 of them could possibly pose a threat to Earth. Those are what we call potentially hazardous asteroids. The potentially hazardous asteroids are actually objects that come within half a AU, meaning half our distance between the Earth and the Sun. That's a huge margin. So it's a 1%. When we say potentially hazard, things that have a greater than 1% chance of striking the Earth. And so there's actually a whole scale of potentially hazard asteroids, and we can rank them depending on which ones really pose a threat. So each of these near-Earth asteroids, different colors that you see here actually represent different groups of these, what we call NEAs, or subgroup PHAs. And they all, the three groups are what we call Atens, Apollos, and Amors. Atens, it all depends on based on their orbit range, how elliptical the orbit is, and then how close eventually they actually do get to Earth. Now, a lot of these groups are not considered what we call main belt asteroids. You're not going to find them in nice stable orbits between Mars and Jupiter. If we were to speed up time here just a bit, let's travel. We'll go kind of slow here, just kind of get these going. Let's speed that up just a bit. And I'm just going to use my mouse to kind of move us around here. So here they are kind of heading off into orbit. And if we get a little bit closer to the Earth, that red region is right where the Earth is. That little orbit right there. We're kind of off axis to kind of help us see where these orbits go. So let's actually go a little bit more on the other side here. And if I were to speed this up even more, I think you would actually really get a sense of how many actually might cross the Earth's orbit. So we're going to go a little bit faster. Again, they just have to come close. Again, over 2,000, we've cataloged over 2,000 of these that might intersect with the Earth. So there you can see a couple of these dots getting fairly close. But they look like they're really close, and they're in fact millions of miles away. So it just so happens that they look very close to the Earth's orbit. But in the grand scheme of things in our solar system, I guess it is fairly close. Again, these are a lot of what we call potentially hazardous asteroids. Okay, so let's stop this from spinning here, and let's go fly a little bit back out. Now, there's actually a whole website dedicated to finding these and cataloging them and trying to figure out if they do potentially pose a threat to Earth. You can actually see an updated version of those charts on spaceweather.com. It's a great resource to find updated asteroids that are making close flybys of the Earth. It tells you usually the distance in what we call lunar distances. So if you see less than one, that's coming between us and the moon. And you're looking at anywhere from 0 to 250,000 miles. Most of them are actually much further out. When you get into the millions, you're looking pretty far away from the Earth and has a lower chance of striking the Earth. Okay, on to our next kind of group or category here. We're actually going to look at Trojans. And that's these kind of oblong regions here. And I put on a bunch of different other categories or other asteroids here listed. Let me kind of zoom out here so you can see it. Now, many planets have what we call these Trojan asteroids. They're gravitationally bound in just the right distance in front of the planet's orbit and behind the planet's orbit, roughly around 60 degrees apart, where they can actually be in nice stable orbits around the sun and not kind of move out of these. Jupiter has some. We just recently discovered Earth has some. Mars definitely has some. So does Neptune and Uranus. So a lot of these planets have these regions. And you see we've designated with these little kind of lobe features. And again, these sit front and behind about 60 degrees apart. Again, if we speed up time again so you can see this, and I think we're going to have to go a little bit faster here. We're going to go pretty fast. And so you can actually see that, again, on either side of like Jupiter here, they don't stray very far from the planet at all. They actually stay right there in a nice stable orbit. All right, let's go and stop that. So this is, again, what we call these Trojan asteroids. And they're actually what we call these Lagrangian points. It turns out that for the Earth, and we were never send satellites that we want to be in a nice stable orbit around our sun, we can send spacecraft to these Lagrange points. And we know that they're going to stay there in that nice stable orbit due to the gravitational interactions between, like, say, the Earth and the sun. They will hang out there and not move and just be in a nice stable orbit around the sun, independent of Earth. So we've actually sent spacecraft and other kind of satellites to those Lagrange points on the Earth. So our next kind of feature we're going to be picking up here as we go along. Our next feature is this region here, just past the orbit of Saturn, out to a little bit past Uranus. These are what we call centaurs. And for the longest time, we thought, okay, these are probably asteroids that got kind of pushed further out by the gas giants. When they formed, they kind of pushed the lighter material out beyond the outer reach of the solar system. Turns out these are highly elliptical objects, and in fact, most of them are not asteroids, they're actually comets. And we're actually going to pick up comets. I won't have enough time to actually go into. I want to kind of keep it under 45 minutes today. But we'll be talking about comets next week and looking at missions to comets and what we've learned so far about some of the comets that we've discovered recently. But a lot of our short-range comets actually come from the Centaur region here, just past Saturn and Uranus. And again, these are highly elliptical orbits when objects are in this region. And so, like, for instance, a comet, Halley's Comet, comes around every 75 years. That's actually a nice short-range comet. Many of the comets that we're discovering are from way out, like the Oort cloud or our next region called the Kuiper Belt. Those can sometimes take thousands of years to come through. And so these are actually nice short-range comets in this region. So that leads actually to our next region, and that is, of course, our Kuiper Belt objects. So let's fly out. These are objects out past Neptune. They're mainly covered in ice. Of course, a very famous object is discovered in this region, of course, is Pluto, and we're going to be visiting that in just a bit. Many of our dwarf planets also, of course, lie in this region. Pluto, of course, was the first true Kuiper Belt object actually to be seen. They thought, of course, it was classified as a planet for the longest time until we reclassified it as like, well, there's actually a lot of objects out here where Pluto is. Pluto does not have a nice stable orbit. It's highly elliptical. It hasn't cleared out its debris field, so again, that's why it was declassified as a dwarf planet. In fact, we've found many other objects, about 24 other objects in this region. Some quite big, not as big as Pluto. Pluto is by far the largest in this region. But for instance, we found an object, which is our second object we discovered here, called Sedna. And it's about 3/4 the size of Pluto, and it was actually discovered in 2004. It's highly elliptical, and it's really far away. In fact, it takes over 10,000 years to orbit once. So Sedna is about 1,100 miles across. And it ranges from basically its closest approach when it's what we call perihelion is about 8 billion miles away from the sun. Remember, Pluto is about 4 billion, so this is twice the distance at its closest approach. Its farthest point away from the sun takes it to 84 billion miles. So you're talking a discrepancy of about 80 billion miles from its closest approach to its farthest point. Highly elliptical, again, would not even be close to be considered a planet if it was by itself because of its high elliptical orbit. The sun from this region actually appears so small, it just appears as a bright star. Again, not much light, so it's really hard to find some of these Kuiper Belt objects. And if we kind of take a look, let's take a look at some of these orbits of these dwarf planets. And here we have them listed. I also have the labels on there. There you can see Pluto. We're going to be visiting. Of course, Starry is also considered a dwarf planet a little bit closer in. You got Haumea, Makemake, Eris, which is one of the farthest ones out. Way ahead of the farthest reaches. Again, we're still learning a lot about these dwarf planets way out here on the farthest reaches past Pluto. But if you kind of take a look and see that most of the orbits of our planets lie in the same plane, look at the Kuiper Belt objects, highly tilted to that of the rest of the planets. So they do not behave like the planets of our solar system. So the Kuiper Belt region has some very interesting things, a lot of comets, and a lot of what we call larger objects like Pluto. Let's go take a visit, actually, to Pluto. So let's take these away. Let's fly into Pluto and take a look at its moons. We have actually discovered 5 moons around Pluto. It'll take just a bit as we get here. There we go. We're coming in on the dark side of Pluto. And of course, New Horizon visited Pluto a few years ago. Did a nice quick flyby because it was traveling really fast, too fast to actually slow down. And actually what I'm going to do is I'm going to speed up time because I want to actually see some of the surface detail that, there we go, right there, that New Horizons captured. So we're actually able to map the latest imagery here on our model. There you can see that heart kind of shaped feature, this kind of large glacier there on the surface of Pluto. Now, longest time, astronomers thought Pluto was kind of a dead, cold world covered with probably just, ice, of course, as hard as rock. We definitely thought nitrogen formed a layer of ice here on the surface, which indeed it does. Remember, nitrogen makes up most of our air here on the Earth. Out here, 4 billion miles away from the sun, it's frozen solid on the surface. Water ice is hard as rock, like here on Earth. Here on Pluto, water is actually hard as rock and forms many of the mountains. But we have found a dynamic world. It is not a dead world at all. This large ice feature here on the surface is fresh, new material. It's changing. It has kind of these glacier features like this hexagon shape, meaning there might be some type of convection happening, something liquid, moving the ice from deep below the planet's surface. Again, we're still learning a lot about Pluto, but it will take future missions to actually go back and take a look. Of course, it might be a very long time. We're still kind of digging through the data that we got from New Horizons, of course. It's still coming in. But then you can see lots of craters, but some of these features on the surface are new features. And when we say young features, it might be within thousands of years, but it's not really old material. So there's fresh material bubbling up the surface from somewhere. And we have detected volcanoes here on Pluto, a very tiny atmosphere, very thin atmosphere. But in fact, New Horizons did discover that atmosphere here on Pluto. So let's zoom out just a bit. So again, Pluto continues to amaze us, as do many of the objects here in the Kuiper Belt region. But we're going to look at one more feature here, and that's going to lead us into next week. And we're going to look at some of the smallest objects in our solar system. Of course, as they come in, they grow tails. And there's actually one right now coming in, flying around the sun. And that's, of course, the comet Swan. So let's fly out of Pluto. Let's head out to the farthest reaches of our solar system, because the Kuiper Belt, again, is pretty much still within the plane of our solar system. This next kind of feature I'm going to talk about is called the Oort cloud, and it actually forms a halo around our solar system, and this is the home to all those long-range comets. So all these little tiny dots as we fly out here, again, form that sphere around our own planet. I'll let it finish moving here because it can get kind of dizzy. But all these little dots are actually comets. And we have classified now over 3,600 or so comets that have been classified and named after the discoverer. You can it's hard to see and make out what's really going on here. But these are these stretch out to about 1 light year away from our sun. And they almost extend out just to the farthest kind of reaches of the sun's gravitational pull. In fact, any passerby of another star could easily disrupt this and send comets in, which happens a lot. Anytime the sun, as it moves through our galaxy, moves through the interstellar medium, as we call the space between the stars, like in the Milky Way, the actual plane in the Milky Way, it sometimes, the Oort cloud, as we call it, disrupts a little bit. And sometimes some of these objects come flying into the inner solar system that we haven't seen before. And usually when objects do that, they're covered in a thick layer of ice. And that's when we get some of the brightest comets that we've seen in our history, because they probably haven't been to the inner solar system in a very long time. So when they come in, all that hard ice starts to sublimate. You get a nice, beautiful tail. And for instance, like Hale-Bopp. When Hale-Bopp came in, it was actually nicely visible in 1998, 99, for those who remember that. So those are the Oort cloud. Again, we're going to focus on the comets and the Oort cloud next week, and even look at some visitors that might have come from other solar systems and other stars. We'll save that for next week and take a look. So I hope you guys enjoyed this evening, and I hope you guys enjoy your weekend and try to stay safe and enjoy phase 2 of our reopening here in Central New York. So again, thank you very much and have a great night.